So now we're just going to briefly look at some less formal aspects of classification, especially when it comes to deciding how to classify and how to train the classifier. So I'm going to talk a bit about Bayesian learning and the difference between maximum likelihood estimation, which is what we've been doing so far, and the maximum a posteriori that we use in Bayesian learning. So this will be just a brief overview, because we're not going to focus on Bayesian learning, but just so you understand a bit the difference. We're going to see also briefly the problem of trying to compute prior probability distributions for Bayesian learning, and also less formally a more generic problem of the difference between classification error and the actual cost of making errors, because the classification problem may not be symmetrical, and some kind of errors may be more costly than others, and how we can take that into account, and also take into account our confidence of the classification. So let's start with this part of Bayesian learning. We found parameters in general so far by maximizing the likelihood. So the probability, the joint probability of having our data and in those classes that we assign them to, given our parameters. And that's how we find our parameters. We find the parameters that maximize that probability, so the maximum likelihood parameters. Basically, we start with the joint probability, but we can rewrite that as a product of the probability of the sample of features that we have in the set that we're trying to classify, or our training set, and the conditional probability of each class given those features. And since this does not depend on our parameters, because the probability of drawing some data from all possible data points does not depend on our parameters, or the parameters we're trying to fit, we can focus only on the likelihood part. That is, the probability of having those classes given the features that we have for each set of parameters. This gives us the likelihood of the parameters, and we find the parameters that maximize this likelihood. So, under a frequentist interpretation of probability, our parameters are not random variables, because a random variable is something that can come up with different values in each trial, and probability is the frequency of the different values over infinite trials. And our parameters will not be something that is random, that comes up differently at each time. So we are assuming that there are some correct parameters somewhere, and we're trying to find those parameters that maximize the likelihood to try to approximate those correct parameters. So basically, the true set of parameters, theta, is something we do not know, but it's not random, it's fixed. However, we can have a different interpretation of probability. So if we use a Bayesian interpretation of probability, probability gives us a measure of our knowledge of something, or our uncertainty, or our rational expectations about some value. So in that sense, the set of parameters can be another random variable, just like anything else, because randomness here refers to our uncertainty about the value. It does not matter if they really come up with different values in different trials or not. The only thing that matters is that we don't know for sure what the value is. So that's a random variable. And if we have a prior probability distribution for our parameters, and we have a sample that we can use to evaluate our hypothesis, our set of parameters, we can update our posterior probability distribution of the parameters given the sample using Bayes' rule. So basically, we have this prior probability of the parameters multiplied by the likelihood of our sample if our parameters are true, and this divided by the probability of having that particular sample. So we can say that this marginal probability of our sample is the evidence here, but in any case this does not depend on our parameters, so we can do the same thing as we did before and ignore this one. But we have this is the likelihood, which is the same thing we use when we do the maximum likelihood estimation, but we also have this prior probability. So basically we have the likelihood here, which is the probability of having the class, given that we have some set of features, but in this case the parameters are also another random variable here. So it's a joint probability distribution of the parameters and the features. And we have this prior probability of the parameters here. So we have this significant difference between the Bayesian approach and the frequentist approach. Using maximum likelihood estimation, we are just changing the parameters because we assume they are an unknown but fixed value, and we are maximizing the likelihood of having this epsilon, of having these classes, given that the parameters are those that we have. But with the Bayesian approach, we have this maximum a posteriori estimation, which is the a posteriori probability of our parameters, our parameter distribution. We maximize this likelihood of both the features and the parameters we are trying. So the probability of the class given this joint probability distribution of our parameters and the features that we have in our data, and this multiplied by a prior probability of our parameters. So the difference here is that the parameters are another random variable, and we have some prior probability distribution about what the parameters would be. This does not appear here in the maximum likelihood estimation. So one thing that we all often have to do when we do maximum likelihood is to use regularization. We use that trick, for example, of penalizing with the squared value of the size of the coefficients or something like that, which actually is something like trying to put into this maximum likelihood estimation, or force it there, some assumption about what the parameters should be. If we're trying to force them to be small, it's because we think it's more reasonable to have small parameter values than very large ones. So in Bayesian learning, we are actually doing that explicitly there. We have some prior notion about what the distribution of the parameters should be, and we include that explicitly in the probability calculation. So basically, we see that this inclusion of a prior probability distribution for our parameters acts as a more explicit and more rational way of regularizing the training of the model. So now one problem that we have is, and that is the big problem with Bayesian learning, how do we estimate this prior probability distribution of the parameters? There are basically two possibilities. We can try to use an uninformative prior probability distribution. This is a prior probability distribution that will not result in a different result compared to maximum likelihood. So often this can be, for example, we assume that the parameters are uniformly distributed. So we have no preference for any value, and this works as maximum likelihood without any regularization. But sometimes this will not be the uninformative assumption. For example, suppose that we have a linear regression where we have one of the parameters is the slope of the line, of the straight line that we are adjusting. If we have an horizontal line, the slope is 0. If it's at 45 degrees, the slope is 1, then 2, 4, and so on. If we assume a uniform distribution of the slope, we'll be looking mostly at nearly vertical lines, because nearly all the values, of the large values, the line is almost vertical. And only values of 0 or 1, we have a line that is more horizontal. So this would not be a reasonable assumption about the parameters, just giving a uniform distribution of the slope. We should give, for example, a uniform distribution of the angle of the line. But this now will give us a more complex expression for the slope, and now we need to sample with that probability distribution different values of the slope to compute the probability and the distribution, the posterior distribution of our parameters and get a point estimate, the one corresponding to the maximum a posteriori. And also we may want to include some prior information on the parameters. We may have some prior probability distribution that we have to include there. And that gives us the most computationally demanding part of Bayesian learning, because since we need to use this probability distribution and we need to estimate all of these probabilities, and usually we will have expressions for the probabilities that have no simple analytic solution for expected values, for averages, for standard deviation, and so on. And so we need to do that numerically by sampling. And that's why with Bayesian learning we use a lot of Monte Carlo methods to get large samples of all these probability distributions and then estimate the overall result to get a maximum a posteriori estimate of the parameters. So basically this is just a general idea on Bayesian learning. We are including the probability distribution of the prior probability distribution of our parameters, and this acts as a more explicit form of regularization. If we assume the parameters must be close to zero, then we have this probability distribution and it works to try to bring the parameters closer to zero, or if we assume something else. In any case, we have this added difficulty that these probability distributions may need to be handled numerically. We need to sample a lot of these points to get an idea of what would be the best estimate, and so we need these numerical methods to sample different probability distributions and do all the computation. This is why Bayesian learning is often more computationally demanding than simply maximum likelihood. Now, another different problem, but just to finish this part of supervised learning, is the difference between making errors and the cost of making errors. So we saw so far that, this idea of loss function and error, and so far we've been assuming it's the same thing. So the loss function is the same thing as the error rate, for example, or some measure of the error, because we have been concerned about scoring different types of errors differently. But the loss function is something more general than simply counting the error. It's actually trying to assess the cost of and the total risk of making those mistakes. So suppose that we have two joint probability distributions of the class class 1 given x and class 2 given x, and we want to find some value of x over which we're going to put the examples in class 2, and below that we're going to put them in class 1. So this would be, this is just a very simple basic classifier, so you can imagine that it's just a free sum that is using x to split into two possible classes, and the errors that we're going to make depends on the choice of x. So if this is the probability distribution of x and class 2 and this x and class 1, if we choose x here, this basically gives us the area, the probabilities of mistaking a point in class 2 for class 1, because we are classifying everything here as class 1, and this may be class 2 points in this area, or making the other mistake of classifying points in class 1 as being in class 2. So one way we can do this to try to minimize this error is try to make it so that for all we're going to choose x such that the probability of being in class 1, if it's x, is greater below this threshold, and larger, the probability of class 2 is larger than being in class 1 above this threshold. So basically we could choose our point here, and this way we would minimize the error rate, because we would minimize these areas where we would be misclassifying the example. So this is what we can get if we are just trying to minimize the error. We are adjusting the x so that the error becomes as small as possible. But now suppose that we have class 1 is a cancer patient and class 2 is a healthy person, and we have different costs of making mistakes. For example, if the patient has cancer but we send her home because we think everything is okay, this is worse than doing the mistake the other way around and having to do extra tests to confirm if the person is sick or not. So we can have this loss matrix which gives us, this is 0 if we make no mistakes, but if we make mistakes it can give us different costs depending on the kind of mistake that we make. And now instead of just minimizing the probability of making mistakes, we want to minimize this loss function, so the cost of making these errors. And if we do this, then actually we get a different result. This would be if we just minimize the classification error, but this would be if we take the cost into account. And we can see this intuitively if we multiply the probability distributions by the cost of making the errors, and then we see that this the first one, when the person has cancer, becomes relatively much more important. The other one just gets multiplied by 1, but this one by 5. And so this is why we now have the best points for doing this classification here. So this is something that we're not going to focus in practice in your assignments, but it's something that you should bear in mind. For the kind of toy problems that we haven't been considering the actual costs of making mistakes. But sometimes the function that we need to minimize is not really the error, the probability of making a mistake, but the kind of mistakes that we're going to make, and they may have to weigh differently in the final result. So if we take into account the expected loss, which is the probability of making a mistake multiplied by the cost of the mistake, and that would be what we should be minimizing in general. Of course, if the cost of mistakes is the same for both sides, then we can ignore that, but if it's not the same, we should take it into account. This sometimes appears in the literature not as loss, but as utility. It's the same idea, but utility is something we want to maximize, loss or cost is something we want to minimize. So basically, you just turn it around or change the sign, and in this case, we want to maximize it instead of minimize it. But the idea is the same. We want to take into account not only the probability of making mistakes, but the different cost of benefits or benefits of getting something right, or the cost of making a mistake. Another problem is the confidence in our decision. We can choose a cutoff point, a threshold where we classify in one side or the other, but there may be different regions where we can have more confidence or less confidence. So let's say we have this distribution of values for a point. We can put a threshold here, so if everything is here is above this x value, we classify it as the black class, because this one is the one with the largest probability. If it's below, we can classify it in the blue class. However, there is a region here where things are are a bit risky. So classifying something here as the blue class is not very good, because our probability of being blue is not that much higher than being black, and it's not very high. So we can choose some region or some threshold below which we simply reject the classification. That is, our classifier says, I don't know, this one I'm not sure. We can use that with estimated confidence values, with the probabilities, for instance, in the logistic regression. We can do that by seeing the proportion of mistakes in classification in different regions or something like that. But there are many ways of doing this, but the general idea here is that we can build a classifier so that in some cases it simply does not do any classification. It says, I don't know about this point because the confidence here is very low. So this is another possibility that we are not going to use in practice, but I'd like you to keep in mind that especially if the risks are high, we could build our classifiers so that they have some kind of modesty built in, and are not always sure about the class, but sometimes they say this is a very low confidence prediction, so I'm not going to predict anything. So basically, this is a very short and light lecture, this part. This is the end of supervised learning. We're going to start with unsupervised learning next week, but for this part, basically, I just wanted you to have a general brief idea about Bayesian learning, Bayesian interpretation of probabilities, and also how the prior probability distribution can replace the regularization that we often use. and also the difference between this maximum a posteriori estimation and the maximum likelihood estimation. And we also saw some problems in decision. What we do in the actual classification, what we are trying to minimize, if we take into account the cost or not, and when we get the results from our classifier, if we really trust in those results or not. So depending on the classifier, there are ways that we can measure the confidence, and we can set a cutoff point and say that below some confidence we are not going to risk a classification. So here are some sections where we can read more about this, and that's it for today.